part-time working in my group 2 years ago. Actually, I think it was 3 years ago. Then it was full-time as a researcher at the Italian Research Council down in Naples, before he actually got his PhD in applied physics at the University of Pisa. And he's doing a lot of very nice work. In fact, I think what he did for his PhD is something that unfortunately, very rarely happens these days. He built his own instrument, the Anson, with his own hands. I must say, I did myself with my ruby laser, because then it was very expensive to buy ruby laser, so my advisor told me that you can build your own ruby laser. It took me a long time, of course. So it's a good thing. You should do this more often, right? So in my group, he's done some very beautiful work on polaritons and other stuff. He's now working with Phil Kim's group and other in my group working on the propagation of surface wave at the interface between 2D material. He's an expert in near-field scanning optical microscopy, and recently he has been really working with others, including Bill Wilson, really going a step further in the relatively novel technique that I think really opens up a new area of research. So without any further delay, welcome.
Thank you. Thank you for the introduction.
So I had to leave earlier, unfortunately, so don't interpret it as I'm not interested, okay. Right? And you can handle all the questions at the end, right?
Okay, sure. So yeah, as Federico said, I mean, I was here since last 3 years basically, but in July I joined CNS as senior scientist, and this is more or less the people that I closely work with every day. And so what I'm going to speak about today is basically something related to imaging in microscopy, but a new technique that we are trying to push and develop at CNS. So I think that everybody knows about the diffraction limit, that the standard optical microscope that use objectives or lenses is actually limited by the diffraction limit of light. So whenever you have an aperture, a finite dimension along the light propagation, you get diffraction. And this basically the main point of the diffraction is that far from the aperture that produce diffraction, you have features that does not immediately represent the shadow of the projection on the aperture. It's a more complicated kind of pattern in 2D. For instance, this is the results of a circular aperture in the light path, and you get these kind of rings. So this is to say that even if you have just a point-like source, and you are watching to a point-like source that, by the way, does not exist, of course, through a optical microscope objective, what you get is a finite dimension of field distribution in the image plane. And if you have 2 point-like sources or 2 points of an object, basically you have to decide when you consider those as resolved. So Rayleigh, long time ago, introduced the Rayleigh criteria for the diffraction limit, and say that you consider the images of 2 point-like sources as just resolved when the maximum of the field distribution one just happen to be on the first minimum of the field distribution of the other. In practice, in everyday life, in the observation through an optical microscope, this means that you have a limit on the smallest detail that you can get in the image. And this is more or less 200 nanometer, because this limit is related to the wavelength of the light that you are using. It scales with the wavelengths, and to the numerical aperture of the lens. But basically, you cannot exceed 1.4, 1.5 numerical aperture. So even at near UV light, around 400 nanometer, you can get at the best half in the diffraction limit. So half the wavelength, that is around 200 nanometers. But by the way, this is how people survived for 200 years and how science has been produced, especially biology, for 200 years. So it works fine. And especially because it gives you direct images. I mean, you can go to an optical microscope, put your eyes or a camera, and you have a look at a magnified image of an object in a field of view that is hundreds of microns. So it's an image, okay? so the people start asking if you can somehow break the diffraction limit in terms of imaging. And this is possible, and the techniques has been started developing 30 years ago, more or less. But you have to give up something. So the way to break the diffraction limit is to give up the direct imaging, the direct observation. You don't look at the surface directly. You don't just take a picture, but you have to do something else. You have to come with some kind of probe, this yellow kind of spot, close to the surface, and try to monitor a kind of interaction locally, whatever it is. The important point is that this interaction is localized and depends by the probe dimension, so that you can engineer the probe to be small, actually smaller than the diffraction limit. And then what you need to do is to move the probe on the surface, okay, to map in 2D the surface for that particular quantity that you are monitoring. This is basically the base of scanning probe microscopy in general. So in the years, people developed different scanning probe microscope. The very first was scanning tunneling microscope that monitor the tunneling current between a sharp metallic tip and the atoms on a surface. But this is quite limited to metallic or conductive samples, and you need or most of the time to operate under vacuum. Then people came up with another instrument that is the atomic force microscope, where basically you don't need conductive samples. You can apply the technique to almost any surface, even to cells, living cells, and we will see more in next steps, because this is crucial for the technique that I'm going to present today. But either in the scanning tunneling microscopy and the atomic force microscopy, do you give up something else? You give up the information about the optical properties of the surface, the optical properties of the material, because either the scanning, the STM or the AFM, they don't employ any light. So you don't get any information on the optical characteristics, parameters like refractive index, polarizability, absorbance of the sample. So there is another technique that can still give you optical information on the sample surface with a resolution that is comparable to the other two. It is the scanning near field optical microscopy. So we are going to basically move in this field today, the scanning near field optical microscopy. The very first implementation was this kind of probe. It's basically a fiber, optical fiber, a normal, very normal, nothing special, but on one end, it's tapered and is coated with the metallic coating, and then at very apex of the tip there is a aperture. So again, now we have an aperture, and then we inject the light through the optical fiber. Some of the light go through the very end, some of the modes, and you have an aperture. So it's very similar somehow to the diffraction by an aperture that I showed at the very beginning, but this time it's useful. It's not the limit, because this aperture is now below, basically it's smaller than the wavelength. So you get diffraction from something that is smaller than the wavelength. When you do this, actually, the field that propagates after, it's very weak. It's a small percentage, but most of the light is in a state of high spatial frequency. That means the near field, the so-called near field, something that does not propagate. You see a picture in terms of this bright red spot, because it's something that stays close to the aperture. So now you can put this aperture in contact with the surface and scan the surface, illuminating locally the surface with basically a resolution that does not depend by the wavelength anymore, but basically by the diameter of this aperture. And this is typically around 50 nanometers. So this is the basic, this is the principle, this is how people implement first the near field optical microscopy. So again, it's a scanning probe microscopy, you don't have direct imaging. You need to scan and make a map of the sample surface, but you locally illuminate with the near field source the surface. And then once this localized source illuminates the sample, you can collect the light, basically, let's say in reflection or scattering from one on the side, or if the sample is transparent enough, you will get some signal in transmission. Is that clear? This is really the kind of basic of the technique. However, I said this is the resolution here is not limited by the wavelength, but there is the aperture that is still limiting the resolution to something around 50 nanometers. So you could say, okay, today I can go probably 10 nanometers in this aperture, but you have a limit that is then that you still need to detect the light, because the light signal here is very low. I mean, the kind of numbers that I can give is that if you launch 1 milliwatt or to the fiber, you get 1 nanowatt at the output. That means a drop of 10 to the minus 6. It's very low to do anything. So if you reduce the aperture, potentially you get higher resolution, but you have to deal with something, with a signal that is in the range of fraction of nanowatts. That becomes serious concerns, because there will be probably background that is higher. Okay? So what was the next step in near-field microscopy? By the way, this works, for instance, also for collecting light through the fiber. This is an example of a map of a surface plasmon polariton on a structured gold surface. But what was next? Well, next step was to eliminate the aperture and try to gain something resolution. And you can do that if you now change to just a AFM cantilever. So this is a normal atomic force microscopy cantilever with a tip, and this tip now can be very sharp, probably 10 nanometer in the kind of effective radius at the very end of the tip. Then when you shine light, for instance, with this parabolic mirror at the apex of the tip, what you get is that locally you will induce a dipole, oscillating dipole, that works as secondary source of field, basically, and it's this near field from the dipole that you are going to use. And you can describe basically this kind of interaction as a dipole kind of interaction, where one dipole is the induced dipole, the other is the dipole induced, the imaged dipole of the tip in the material. So at this point, at these distances from the surface that are the order of 10 nanometers or so, you don't even speak about just the polarizability of the tip or the polarizability of the material, but what you end up is a complex overall polarizability of the junction, of the region that includes the very end of the tip and the surface and what is in between. So this complex polarizability or effective polarizability include the tip and sample parameter. And what is important here is the dependence with D. D is the distance of the tip with respect to the surface. And I'll show you why it's important. So again, in this scheme here, if you then collect the light that is scattered by this region, your resolution is actually limited by the localization of the interaction. It is basically close to the diameter of the tip end. It can be easily 10 nanometers. So the resolution is better than an aperture SNOM. This technique is, by the way, called apertureless, because there is no aperture defined in the field. And basically, it still does not depend by the wavelength, because here there are systems that have been coupled to synchrotrons, for instance. The resolution is still limited by the tip, not by the radiation wavelength itself. So high resolution, but what's the problem? It's the background, because nothing here is really point-like. everything, the tip and the beam spot, has some finite dimensions. So when you collect the light in this configuration, what you get is the signal that you wish to detect. This is a signal that is scattered by this region and has this dependence with the distance. But you also get a huge background due to the scattering from other part of the tip, from the sample, and so on. So you have to detect this weak interaction, this weak kind of signal with respect to the background. And this is where this dependence by the distance comes, because it's nonlinear. So if you work in tapping mode, that means the tip is going up and down, this signal is going to be modulated at the frequency of the tapping. But since it's also nonlinear, there will be probably higher harmonics in the signal that you detect. And this is basically what people have used to distinguish the localized interaction from the background. Building, this is a kind of, this is called pseudo-heterodyne detection, where you have basically an interferometer. So the source goes to the tip and goes back, is scattered by this region here, and goes to the detector, as well as a reference beam that goes first to a mirror that is mounted on a piezo scanner and goes back to the detector. So here in the detector plane, you have interference between the light that is coming from this region here and the light that is back reflected from the mirror in the reference beam. And this produces some fringes. But since you have nonlinearity in the dependence of the near field, you have also some sidebands if you start oscillating the mirror. So this is basically, people have found that the sideband at the mirror, or produced by the mirror oscillation in the reference, is actually higher than the harmonics itself. It is basically, this is what contains mostly the near field information. So you can actually filter out, and from this scheme, you gain also something else, because now you can use a lock-in amplifier to analyze this modulated signal, and what you can get, as in this case, actually in this case, it's the amplitude and the phase of the field, not just an intensity map, but the map of the amplitude and the phase as well. And there is something more, because now if you have a parser laser and at each point you do the Fourier transform of that signal, what you get is a spectrum information that is very similar to a FTR, but it's at the nanoscale, because the signal is coming from a region that is localized under the tip of the AFM. So this is basically a kind of overview of how near field, the two main near field techniques work. That is the aperture techniques based on the fiber with an aperture, and this the scattering SNOM, or the apertureless SNOM, that is this other kind of setup. But both of them basically are based on the local illumination and the detection of the light. However, I said that the core of these kind of near-field optical microscopes is an AFM. So it's an AFM cantilever. That means it's an AFM. There is a system that stabilizes the cantilever there at that distance. It is an atomic force microscope. So on the other side, you have a atomic force microscope, and I stress the force, because this is what we are going to use in the new technique. So this is a very general scheme of how an AFM works. You have a cantilever with a tip, and then you have a laser that illuminates the back of the cantilever. It is reflected and goes to a 4 or 2 quadrant photodiode. So as the tip bends, due to the interaction with the surface, basically the deflection is amplified by the light path here, and this is read as an imbalance between the upper and lower part of the photodiode. And this is very powerful, because it looks simple, it is actually simple, but allow you to easily detect the forces of the order of piconewtons. Okay? So usually when you go to the lab for, and especially for AFM users, what you do is most of the time to take a topography of the surface, no? Out of AFM, you get the topography. This is the main information. But actually what the microscope is doing point by point during the scanning is to keep constant this force, this interaction, to a value that depends strongly by the tip and the humidity and also by the sample surface. So this is a typical force that a tip experiences by approaching to the surface. Let's assume this is the surface and the tip of the FM is here. When you move down toward the surface, this is the kind of force that the tip experience. There is a first a non-contact regime or attractive regime that is dominated by van der Waals forces. And then as the tip goes basically superposed to the sample surface, you start in a repulsive regime where you are dominated by finally by the Pauli repulsion between the electron clouds. But this is basically what every time that you go to use an AFM happens. So on one side we have the goal from near field optical microscopy to try to get imaging, an optical image of the sample surface with let's say nanometer resolution. Okay. On the other hand, you have a powerful force sensor. Can we combine the two of them? Basically, I mean, still illuminating the surface, still try to get optical information out of this illumination with nano resolution, but we don't want to detect any light. We want to use the AFM there as a force sensor. What we can get. So this is how the title of the presentation comes. It would be a photon-less, because you're not detecting any light. Optical, because you still want information, the optical characteristic of the sample, with a resolution that is in the nanometer range. So there is actually a first example that is commercially available of something that is going in this direction. Is this microscope, a so-called photothermal microscopy. There is something commercial for analysis, and it works like this. So you have, in this case, a contact mode AFM. That means that the tip goes very close to the surface, mostly in a repulsive regime. It's not vibrating by itself. It's just approach to the surface. It's the so-called contact mode AFM. Then what you have is a laser in the mid-IR, something between 5 and 12 micron in wavelength, that illuminate the tip sample region. It is usually pulsed at a rate of 1 kilohertz. Okay, most of the time it's a broadband OPO, a optoparametric oscillator with 10 nanosecond pulse and 1 kilohertz repetition rate. So you have this tip in contact here, and you have this mid-IR radiation illuminating the region there. So what happens is that if the sample absorbs some of this radiation, it's locally going to expand under the tip. And if your feedback, the feedback that keep the tip sample distance constant, is actually slower than the repetition rate, actually this expansion modulated at the same modulation frequency of the laser, it's going to kick the tip from below and induce some oscillation here on the tip. And these oscillation, the blue, that is nothing else than the oscillation that the 4-quadrant photodiode read through the optical level from the back of the cantilever. Now, if you change the wave number of the illuminating light, or if your sample absorbs more, the oscillations are going to be larger. Okay? And this is the principle. If you hit the resonance of the sample, if you locally hit the sample, you can read that information in terms of a local expansion, in terms of a oscillation on the tip. And this is what you can monitor during scanning. For instance, you can get something like this, where you have some PMMA in epoxy, and if you use 1730, that is the CO vibration frequency, you can get an image where you basically highlight the PMMA with respect to the rest of the material. Or if you point then the tip in one position, you can sweep the wave number with the wavelength if you want, and you get a spectrum that is equivalent to a FTR spectrum in the same basically working region, but it's local. It's from that region. It's not from a large 10 micron whatever spot that is a typical FTR. The resolution again here basically is related to how to the thermal constant of the material, not only to the tip sharpness, because it depends. If the material expands more, you have a stronger signia. If it expands less, actually you have a lower signia. Also, if it dissipates heat faster, you have a lower, less resolution, and so on. But this is a kind of naive and trivial way to describe the technique, because actually this is a physical expansion. The sample is really eating and expanding. Can you do better? Can you move to a regime where you detect weak interactions and you can start to speak about forces more than a physical expansion of the sample? Well, it has been demonstrated by Belkin that you can do better by moving from this kind of regime where you have an OPO that is 10 nanoseconds in pulse and 1 kilohertz to something that is a CW laser, like a QCL, that is modulated, but it's modulated at a specific frequency, the resonance frequency of the cantilever. So if you hit the frequency of the cantilever this way, you can basically avoid the damping of the oscillations after each pass of the laser, and you get from this regime to this other regime where you basically have continuous oscillations. And this means that when you try to get the signal out of here, actually the amplitude of this oscillation, this gives you better signal to noise ratio than just trying to get the information out of this. And this also means that you can lower the laser power, you can go in perturbing less the material, and also try to get information out of less material itself. And actually, this technique has been used to probe a single layer, basically a self-assembly model layer on a surface. This is the chemical contrast that they get. This is the topography, and this is when they go to a vibration mode of one of the molecules of the PEG. So here, I mean, you can say, okay, but so far, basically, you always presented the example where you are resonant with the sample absorbance, okay? This is basically what this is based on. But in general, when you look through a microscope, an optical microscope, you get an image whatever it is, no? The sample, and whatever it is, the light that you are using to illuminate it. So can you somehow do a better job of trying to be more general in the technique? Like, can you use a kind of photon-less technique to try to get optical parameter, not necessarily be resonant with the absorbance of the material, not necessarily heating the material locally, but in general, for instance, something that is related, getting a contrast that is related to the refractive index of the material. Okay? This is a more general concept than just trying to hit a vibration resonance of the material, getting in a regime where this interaction is kind of enhanced. So the answer is yes, and for that we need again to have a closer look to the atomic force microscope possibility. So usually you don't care about this when you use an AFM in tapping mode. Tapping mode means that the cantilever is oscillating up and down at a frequency, usually the resonance or close to the resonance frequency of the cantilever. So usually you are in this condition, you move the cantilever up and down, and you approach to the surface, and you stop the approach when this oscillation is damped by the local interaction of the surface with the cantilever. And this is how you work in tapping mode, and you scan and you get information, the topography, through the feedback of the AFM. The feedback is the electronic that control the AFM and say, okay, I monitor this amplitude of oscillation and set the distance from the between the tip and the sample in order to keep constant at each point of the scanning, this distance, actually the force. However, the cantilever is an oscillator, it's a mechanical oscillator, and as such, has many modes, okay, of oscillation, many angle modes of oscillation. For instance, there is a second mode that is like this, as a node in the center, has a resonant frequency that is 6.6 times the fundamental frequency of the cantilever. And this is used, for instance, in the multi-frequency force microscopy or in the bimodal, in this specific case, 2 modes, bimodal, where basically you have the feedback on one, so this is what you get in terms of amplitude and phase from this mode, and then you don't apply any feedback on the second mode. You just monitor what's happening at this frequency here. So since this mode during the scan is non-compensated, it's basically free to locally monitor the interaction between the surface and the tip, and you get very high contrast. You can get very high contrast in the amplitude and phase related to the mechanical property of the sample. So this is the basic of another technique that this is what I'm going to speak about here. It's a photo-induced force microscopy. What is the principle? You again have this cantilever, the same scheme of an apertureless optical microscope. You shine light on the junction between the tip and cantilever. This time you don't collect any light. You see, before you had 2 arrows. Now, actually, I should have put at least 1 arrow going in this direction, but you don't have the arrow in the collection direction because you are not collecting anything. But what you are interested is the local force that is resulting from this illumination, because as I said, you can monitor, you can, generally speaking, try to describe this in terms of an induced dipole on the tip and the image dipole on the surface. And out of this interaction, you can get some forces that are driven by light, are due to the light, actually. And in general, you can distinguish between two terms, a local force and non-local force. The non-local force, as you see, just depend by the polarizability of the tip and by the external field, this. But it's non-local, does not depend by the distance, okay? The local force instead depends by the distance, linearly, the distance between the tip and the sample, z, and by the polarizability of both the tip and the sample. So if in the sample you have 2 kinds of material with 2 different polarizability, and the tip is the same, you basically fix this, and you can probe the local polarizability of the sample. This is the idea. I want to let you know that this is not local, and actually for people that use the Cypher microscope that has the blue light implementation, basically where you do the tapping mode using not the piezo to excite the cantilever, but light, it's this force that you are using. But this is just for people that use that specific microscope. So, okay, now we have this configuration, how we probe these forces out of this interaction. So the very first thing that probably you will do is, okay, let's go to the bimodal kind of configuration when one mode is excited by the piezo, dithering piezo of the cantilever, on the cantilever, and the other is locally resonant, with the modulation of the external light. Okay? So basically you have one mode driven by the piezo on the FM and the other driven by light. So if you do this, actually, you can record in the amplitude of this mode something that is proportional to the overall force that is going on. You get something here. But out of that signal, what you want is only the local force. You are not interested in the non-local force because it's a kind of light pressure on the cantilever that you have even if the cantilever is not in contact with the sample. And does not provide any local information on the optical parameters. So how you can get rid of this? So the way is to not directly modulate the light at the second mode frequency, but at a frequency that is a sum here of both the first and the second mode. And then the second mode will be excited through the nonlinearity of the interaction as a sideband. If you do this, basically you can almost eliminate completely the non-local force and just get information on the local force. And this is an example. This is an example of something that is published in literature. There are not many papers published actually so far, where people show that on a copolymer, you can get optical. You can use a wavelength that is resonant on one of the two polymer absorption, and you get an image, and then you can get the complementary image being resonant with the other polymer. So at this point, this is an evidence of the technique, but you should say, okay, all this story, and finally you are again in resonance with the material. So what? So this is what where we are trying to add something here with some experiments at CNS. The good part of CNS is that it's a facility where you can produce almost every kind of sample, and also the other good part is that the research and the people that are around that do research there. So for this specific experiment, we use a titanium dioxide sample produced by Rob from Federico group. So we want a sample that has not specific resonance or absorbance at the wavelength that we are using. We want a sample also where we can easily distinguish between topography and the optical information. This is the best, no? Because you can get always topographical artifacts, something that is related to the non-compensation of the distance between the tip and the sample, but a sample where you can easily distinguish between topography and, for instance, and refractive index. It's a good sample for this kind of experiment. So in this sample, we have squares of titanium dioxide embedded in the photoresist, EBL photoresist, that is ZEP. So they are both almost transparent to the 532 nanometer, that is the wavelength that I'm using here. And since there is an overetching usually in the process, in the atomic layer deposition process that Rob used for this, you end up with the topography where you have a shallow hollow here in the topography. This is a section. But in terms of refractive index, you still have squares in the polymeric matrix. So if you do AFM on this, you see this kind of holes on the surface that has this section. But the SEM shows actually the material contrasts that are squares of TiO2, 200 nanometers large, by the way, in the matrix of a polymer. So now, if you use an AFM in tapping mode, and you look at the phase and the amplitude. I put here these images just to show you that we are basically free from topographical artifacts, because in the phase that is quite sensitive to the material properties, you don't see squares. And the amplitude is almost constant to 0. This is equivalent to the error for the microscope. So the question is now, if this is true, if you are monitoring a local force, and if you are sensitive to the material polarizability, that for this kind of directives close to means basically the refractive index of the material, and since these squares have a refractive index of 2.4, and all around you have almost 1.4, something like that, what is going to be seen in photo-induced force microscopy? Holes or squares? The refractive index contrast or the topography contrast? Squares. So it works. It actually seems that this kind of force, it's what we are monitoring in these conditions, because you get squares that is the right shape where you have the refractive index information. And this is a resolution. This is 35 nanometers, and actually on this other particle I get as good as this gap that is 5 nanometers. So it's at top of the resolution possible with the scanning probe microscopes. I will skip the description here, but because I want to introduce the last concept here. So far we are still speaking on two different materials, no? So you say, okay, but if the contrast is the only thing that you want, there might be other techniques like a bimodal AFM with a very good AFM in some specific condition that can give you some material contrast, even though in that case the material contrast, it would be not refractive index contrast, but it depends what you want. Now I will show you that you can get also kind of unique response in photo-induced force microscopy, even if the material is the same, like MSO2. So in this case, the sample is produced by Luis, that is that, from King group. And this is a CVD grown MSO2, where you have single layer, 2 layers, and 3 layers, this purple here. So the material is the same. What changed here is the number of layers. The question is, are we getting any contrast in trying to scan with the PIFM this region here, for instance, or this region here? Yes. So this is the topography. It's very, the overall variation topography is from 0 to 3 nanometers. You basically have nothing in the phase and the amplitude, but you have a contrast between single layer and 2 layers in photo-induced force microscopy at 532 nanometers. And this is another example, and I will remind you the shape, the kind of relation with the local force, where you have 1, 2, and 3 layers. And actually, we repeat it. If you are, thinking about what is this step, this is the 3D of this. And actually, we repeated this on many areas and different samples. It seems to scale linearly. Now, between 1, 2, and 3 layers. So it looks like more elastic scattering. But actually, to really understand if this is related in this case to any spectral feature of the material, we need to scan the wavelength. We need to change the wavelength and see if there is any resonance in this point. This is still work in progress. We didn't do this yet, but this brings me to the last slide. Basically, what is going next? Actually, it's improving the platform. This is how it was last month. It's already different. This is the FM that is the core of the platform. It's from a commercial FM from Molecular Vista. And then there is all the optical setup around that we are building. And next step is to make this available also for users, actually. And we are going to cover femtosecond laser. because we can plan to do some pump probe experiment, for instance. And actually, this femtosecond laser is coupled to a photonic crystal fiber for supercontinuum generation. So this is where we want to monitor by changing the wavelengths if there is any resonance in the MSCO2 in this case, because with the 532 nanometer we are above the band gap of the material. And so coupling new laser sources, actually more generally probing the limit of this kind of detection, because the photothermal in the weak signals regimes, if you want, and the photoinduced force microscopy are, one is based on the contact AFM, the other is on a tapping and actually bimodal AFM. But even though they are right now working in two different regions, nothing prevents that finally they are seeing the same kind of effect, because even if thermal expansion and optical forces are different, nothing, there's nothing that says so far that the two microscopes actually work in the same way. Okay, so this is what we want to probe. We want to try to understand in which regime you get something more like related to just to the heating, and in which case there are some optical forces going on. And this is the people that so far, one way or the other, contributed to the project. And of course, I want to thank you for your attention. Get any question? Question?
So with these 2D materials, the reason that you get some contrast is because you have some different polarizability, is that what you're saying?
Yeah, that would be, I mean, this is what we hope. Before saying that, I will try to change the wavelength to be at least above, below the band gap, see if there is any change in this contrast, or there should be, and see how this is dependent also by the wavelengths before concluding that we are not in what we are actually probing. But since it's scaling linearly with the number of layers, it looks like it's kind of elastic phenomenon so far.
And the z to the power 4, how does that come in that picture?
Well, the z is constant.
You keep it constant.
But it comes to the fact that it's a local force, because it's z to the power 4. Yeah, sure.
Do you expect any different signals for different polarizations of the excitation beams?
Yeah, this is a good question. Well, if you look at this force here, it says z, no? And basically, this kind of relation is derived by assuming that there is a preferential direction that is the tip axis. This is how basically the force component are filtered out, because in principle you have a tensor of polarizability, and then you extract kind of some components out of that. I tried different polarizations, and it's not obvious that they are really affecting, also because it might depend by the sample itself, because maybe with the directed sample, if you have a tip that is basically one directional kind of antenna, there the polarizability along z can make a difference. But if you have a material that is absorbing, it produces some signal, even if there is transverse components, you can actually apply the different kind of concept. It's the tip dipole that produce an image in the material, or it's the material dipole that produce an image in the tip. So that it's more complex. It does not immediately relate to the polarization of the light, or at least so evidently. So I tried, but I didn't see so far a clear evidence. And it's actually difficult to probe, because what you actually do is that you shine light on the tip, but then you want a signal. It means that you start to move the beam around, try to maximize the signal. So if you have external optical elements that you have to rotate to change the polarization, it may be difficult to reproduce the same exact condition over real alignment and power just by rotating a quarter wavelet, for instance. So yeah, it will take probably some extra time, a systematic study to try to understand. I mean, at least you must be sure that you are in the same kind of photon flux or alignment conditions, even if you change something externally to the microscope. Yeah, in principle, yes, but it's something to test and prove. No other question? Okay. All right. Thank you.